this week we have Romeo Kleitzer here to talk about a project he's just started. It's called OMIT. Romeo will tell us a little more about it. It's the Open Mesh Infrastructure for Telemetry. So it's a combination of a variety of open bandwidth, EM bandwidth to build mesh networks. And so I'm going to turn it over to Romeo to kind of set the stage why this is important for Call for Code and what his project is proposing. So Romeo, want to start off here?
Awesome. Okay, so I'm sure you all know Code for Code. If not, go in the corner. So those are the type of disaster Call for Code is addressing. So hurricanes, earthquakes, floods, volcanoes, extreme weather, and wildfires. I've put some examples from the Google image search here. And one important I was thinking of, which is not really on Call for Code, but it's also important, especially for the Western world, with the addition of more and more regenerative energy sources, is blackouts. So I have found this image, and then immediately John told me, oh, he remembers that day, and I think that's the point where I want to give the mic to John and let him share.
Yeah, so Romeo, very often in whatever natural disaster, whether it's a Hurricane Maria, great example, or anytime the disaster affects the power grid, we have trouble communicating. And if you recall, I think it was in 2002, there was a blackout across the grid in the Northeast power combinations. A bunch of power companies were sharing the grid, and I don't know. Ultimately, it was tracked down to some birds on a power line in Ohio someplace, but it turned off the entire New York grid. I was at the time at the IBM T.J. Watson Research Center, and I was responsible with my teams for the Watson Compute Center. We were running a whole variety of experiments for scientists in the Watson Yorktown Data Center. And when the power went out, we all kind of knew immediately that things were going to go bad quickly because all of our servers, abruptly turned off. And so we ran down to the data center. We were trying to figure out what was going on. First thing that crossed my mind, it being very close to 9/11, was an attack on the nuclear power plant that's not too far away, Indian Point on the Hudson River. About 10 miles from the Yorktown facility. So it was scary for a moment, and then we moved straight into disaster recovery, trying to restore once the grid came back up a day or two later. So it was, and we struggled, right, without power in communications. I think that's what your project's going to address.
That's true. So Sean, I thought you have another.
Yeah, so I also remember this day quite well. It's actually summer 2003 is when it happened. And I was in the Poughkeepsie site. I had a team member in Endicott. We were on the phone at the time talking about project stuff. And all of a sudden he said, oh, hey, that's weird. The power just went out here. And I'm like, okay. And we kept talking. And about like 20 seconds later, my power went out. I'm like, hold on. I'm going to go out in the hallway and see what's going on. It took us like about, everyone thought it was a local event. I'm like, no, I was just talking to someone in Endicott. That's like 200 miles west of here. They just lost power too. Like, this is broader than that. It took us about 20 minutes to realize how broad it was. The telecom network stayed up more or less through this, but it was also a good instance of realizing that your recovery procedures are not always what you expect them to be. So I believe something like half the backup generators at the Poughkeepsie site did not start correctly after this, which meant things like the badge locks for our building, which was the badge lock area that you had to get into to get to the disaster recovery center, was not powered. And so I happened to be like in a window and noticed some people trying to get in and came down and and chat with them. They waved me down to let them get into the disaster recovery center, which they couldn't get into because the batch lock system wasn't powered because the generators didn't all work. They now test the generators a lot more frequently.
A wise precaution. All right, so Romeo, that's a funny story.
Yeah.
Romeo, want to tell us about what you think, how you think your project can help?
Exactly. Yeah. So the idea is the following. Where is my GitHub? So I've created a little GitHub project already, and it's some sort of a meta repository where I will just place the architectural documents, the reference implementations, and the sample code. And the idea is the following. So it is called OMIT for like not delivering a message. So the system is resistant for intermediate nodes in the network not delivering messages. And therefore I call it OMIT, so Open Mesh Infrastructure for Telemetry. So the focus, of course, is on sensor data. As I work for Watson IoT, I have a lot of work with sensors, but also you can use it for text messaging and also for position-related information. For example, in emergency, I can text to the network, I'm here, I need help, or I'm here, I'm having a truck with water and emergency nutrition products, and that's how these messages can spread the network, including position information. And you see here the OMIT layer is only a transfer layer for messages, and on top of that, as you have it in the TCP/IP stack, you can add additional protocols on that layer. For example, for messages which have a confirmation or for encrypted messages and so on. So at the layer down, you have different modulation technologies. So the one I'm showing you later in the demo is called APRS, Automatic Packet Reporting System. That's a ham radio protocol, which is based on modulation, audio frequency shift keying modulation, which is called AX25, which uses the audio frequency band for modulating. Maybe you have had such old modems, they are called acoustic couplers. They have also used this X25 modulation scheme, and AX25 stands for amateur X25. So those I will show you today. Then there's ROS, FT8, and JT65, and that's a new modulation scheme which has been invented by someone who is working with data from radio telescopes, and that's pretty amazing because I have only had a little small antenna, and oh, maybe it's too late. Let's see. It was yesterday evening. Whether I can reload this page and see the connection. So, yeah, here it's working. See? So I'm based in out of Switzerland, and I had only like a 3-meter antenna on my balcony, and I used around 5 watts. And you see here with a JT65 modulation scheme on 14 megahertz, I could reach New York easily. No? So that's more sophisticated, but 14 megahertz is unfortunately limited to ham radio operators only. So I want to make this project more open. So there are 3 frequency ranges which are available all over the place. The most famous one is CB radio, which is on 27 megahertz. And the cool thing about that is, there are 3 cool things. The first, it's available in nearly every country, and you are allowed to build and attach custom-made antennas which have a higher gain, up to 10-fold more reach. And there is this modulation technology called SSB, which supports ROS, FT8, and JT65 as well. And I'm currently working for an NGO which want to use this technology in Ethiopia for villages. So let's see how that works. And by the way, at our Call for Code hackathon or hackathon submission marathon, we are trying to build such a system on top of the Watson IoT towers and do some war driving at night to see the reach of all those different frequencies. The second famous frequency is 466 megahertz, which is available in Europe only, I think. But you get little devices, they cost like 10 to 20 bucks at AliExpress. and you have a half of watt of transmission power. In contrast, on CB radio you can go up to 12 watts on SSB, but we will try those as well. And then you have another layer here, that's ISM band, which in Europe is 869 megahertz. I think in US it's 915 megahertz. And the reach is far higher than Wi-Fi, but still we want to enable Wi-Fi, Bluetooth, and ordinary IP tunneling as well. So that's the layer on the network, and it's open to any other technology. So that's the protocol as it's specified at the moment, and that's an example deployment. So imagine you have a smartphone, so it's all working with only a smartphone if you like. You attach one of those, for example, PMR 466 transceivers to it. Depending on where you are, you have between 3 and 30 kilometers reach. So if you're on 2 mountains, you can go up to 30 to 50 kilometers. And if the other side has the same setup, you can basically send text messages between each other. And here is an example of using Bluetooth or Wi-Fi. So it's a store and forward topology. If you meet someone, you can sync your devices and exchange the stored messages, and then they get propagated. So it's multiple send, and in the nodes, we by hashing the messages, we just ensure that we don't transmit duplicates. But the reason why it's so resilient is that we just send the messages on multiple channels multiple times. In addition, you can create a thing which is called iGate. So here you have RTL 3228, or is it 2832 dongle, whatever. It's a SDR, software-defined radio, which costs also 10 to 20 bucks. You plug it to Raspberry Pi, and you can basically receive anything between 25 megahertz and 2 gigahertz. And that's, in that case, a one-way connection. But of course, with a CB radio, you can do it 2 ways. And that's a bigger range then. And this can be connected to the internet or to intermediate carriers. So for example, you can do CB radio, and you can bridge distances between 20 and 100 kilometers, depending on where you are and what equipment you are using. And that way you can build a solar battery powered mesh network. And the cool thing is, this is already existing, so the proof of concept is already working. There's a system called APRS, the Automatic Packet Reporting System, which is a ham radio technology. But as you can see here, this is, for example, my trajectory in Berlin today. So you see here, I was landing at the airport, and then I took the train, and then I was messing up a bit in Berlin, and it was able to track me. So for doing that, I have used only my smartphone, or it works via internet, a smartphone, or you can connect the app to a transceiver. And I want to show you a little demonstration now, and I hope it's working out. So let me. And by the way, I'm searching for committers and contributors. So I'm even thinking of putting this to Kickstarter also. But just if you are interested, just ping me. Another thing which I haven't checked out, I just want to share it with you, that John told me there's a project called Serval. I will check it out. I think it tries to do something similar, and maybe we can use this as an additional layer. Anyway, so I will now stop sharing and check.
Oh, we lost your voice, Romeo. You went on mute.
Okay, for whatever reason, I went on mute. What I wanted to do. I wanted to show you this app. Okay, so it's called APRS Droid. And now I'm connected.
You want to turn on your video too, or is that something we should see?
Oh, yeah. Can't you see my screen?
Well, your screen stopped, and now we thought we were going to see you.
Okay, so let's try it again. What about this?
Handsome Sean. There we go.
Okay, so this is the app. I don't know whether you can see it. Can you read something on that? Maybe not. Okay, but
Yeah,
let me try
520.
to demo it anyway. So what I will do now is I will pull out to there, and the only thing what you need to do is, can you still hear me? Okay, is to, or maybe do differently. Um, for example, if I want to send my position, I just say send position, and you should hear something. Can you hear that? That's the AFSK modulation, and actually it's pretty simple. You just connect. Of course, there are special cables, but you can just connect this headphone to such a $20 transceiver. And yeah, I don't have reception, so I will ask Miriam to help me. Miriam, can you help me with the laptop, please? So, can you still see me? Okay. So the trick
All right,
is
we're
that
going
you,
for a journey now.
take a video of me. Okay.
Okay.
So I need to go to the window.
Is it recording?
So, oh, it's not raining anymore. Perfect. Okay. So can you hear that?
Yeah, we still hear you.
Okay. So let's wait if you get a message. So this is now the transceiver. It's on a frequency 144.8 megahertz. And here in Berlin, there are some relay stations on top of roofs, and also people who are walking and driving around. And they are all on the same frequency, but you can pick those guys up here. And yeah, we just wait until we hear such a message. In parallel, can you? I will put it here. So.
Okay.
Thank you so much. So you can hear that. And now what I'm doing is I will send my position by just attaching this headphone to the microphone of the transceiver and pushing the send button. And let's see. Okay, I've done this. And you can even, thank you very much. You can even do text messages. So I have a colleague here. He worked for IBM. His name is Ansgar, and I sent him a message through that system, so it really works. And let's see whether this message got picked up. Because let me share the screen again. So can you see my screen? I will now go to the headset again.
Yeah, we see your screen again.
Okay, so can you still hear me?
Yeah,
Good.
sounds good.
So let's see whether, so I have to get rid of John here, sorry. So whether it got picked up. No, so it is between a couple of buildings, so I would have to go to the street. But anyway, you see the trajectory from before. So that's how it works. And the cool thing is there is open, so a non-ham radio system as well, which is called CB APRS, which is already in place. And CB APRS has also a set of those so-called iNodes. So iNode is a APRS node which has an internet connection. No, sorry, it's called iGate, not iNode. And there are RTL 2832 or 3228 dongle-based ones all over the place in Europe, and also real CB radios. So that means you can make use of this system without the ham radio license as well. And yeah, the app is already there. We might need to do a couple of changes, but that's basically the idea. So that's the APRS layer, and also in the Munich hackathon we are trying to use the TI sub-gigahertz and LoRaWAN, for example, the Things network gateways as well, and test whether this works as well. So that means if you have a network partition, some islands which still have internet, or even a wider range outage of communication, this system can really use for emergency and disaster use cases. Yeah, so I'm open for comments and questions. And if not, I think Sean has some interesting stuff to tell about drones, no?
Um, so I got a couple of questions, Romeo, that uh, once you prove out the basic technology of having, building a mesh network, then the applications on top of it. So would you propose building apps here? What's the apps story?
Okay, so
Obviously,
the app,
text
yeah,
messaging.
yeah, the app story, out of the box, you can already use the APRS Droid application, which can make use of internet, which can make use of walkie-talkie style infrastructure. And at the other end, of course, you have the iGates using Raspberries or so. And you can use that to send messages, point-to-point messages, and also to publish location-based information. So what type of resource or thing or sensor value is on which place on the map in real time, and that messages they propagate. The things I'd like to add is store and forward, and also extend the app that an app also can be used as an iGate. That's the first thing, and some integration with LoRaWAN and TI sub gigahertz and wireless. That's more or less the roadmap. And of course, on top, additional layers like guaranteed deliveries and coupling with MQTT so that you can tunnel MQTT through OMIT, such things we can think of. So we are already having a team which comes to Munich who wants to work on that. But if someone is interested, just ping me.
So is it? Tell me, understand that you're proposing a new protocol, or on top of these existing technologies?
Yeah, it's let's say a layer 3 protocol on top of existing layer 2 protocols. And once the layer 3 works, we can think about layer 4. Yeah, and interestingly, there is at that level there is no routing. So that's one important difference to internet, because internet initially was made for disaster use cases, no? But if you just throw a nuclear bomb at Frankfurt, half of Europe won't have internet anymore, no? So it won't work anymore. So this mesh infrastructure is connectionless without confirmation. You just broadcast, and whenever you pick up a signal, you relay it, and it's on a digital channel. No? It's analog transmission, of course, but it's digital relaying, so noise doesn't get propagated. So once you can decode a message, then you start basically with a zero noise level again.
So when I was down in Puerto Rico for a hackathon in June, and one of the teams that was the winner, they were using ham radio. They took a JSON object and they transcribed the JSON into a set of audible tones.
Okay.
And then they transmitted over ham radio the audible tones, and on the remote side of the ham conversation, they captured that particular clip and then transcribed it, the JSON object, which was just an audio set of beeps, back down into into data.
Yeah, that's what we are doing since 50 years. So we started with a technology called RTTY, so radio teletype, and now we are just improving. So there was then a new, so then the king discipline in ham radio operation was CW, no, the Morse code, because that way you could bridge distances which you couldn't bridge with normal audio. But and everybody said, okay, that's the king discipline, you cannot get better. Then there was, I think maybe 20 years ago, a new modulation scheme which is called PSK31. So that was even better than Morse code. And then, of course, this AX25, which came up on the higher frequency bands because you have more speed and more bandwidth. And since a couple of years, you have this JT65 and FT8 modulation schemes, which actually was implemented by a data scientist from a radio telescope. It was also a ham radio operator. And you can go up to minus 30 dB below noise and still can copy the signal, and it has forward error correction. So you get not noise signal, you get the real message, and that's pretty cool now.
That's pretty cool. All right, so what's the next steps for your project?
So the next step for my project is to work with the team at the Call for Code submission marathon on 27, 28 in Munich. And then I will try to get a Kickstarter project running to get some funding. And I already work with the NGO in Munich. They want this technology for Ethiopia. And yeah, I'm just searching for volunteers, for funding, and I'm pretty convinced that we can really generate some momentum with it.
Very cool. So Romeo has answered the call
Yeah,
for Call for
I
Code.
know.
And so that's excellent. So thanks for that's any other questions from others that have built mesh networks? So one question that I'm sure Brian is thinking about, but maybe it's too shy to ask. But when we were working with the sub 1 gigahertz configurations with Texas Instruments, turns out it's hard to set up the hardware, and Sigfox made it a little bit easier. But some of these ad hoc networks, you really do have to work at it. And do we think that you're going to have enough? So how do you make the network effect easy?
Okay. Yeah, so the idea is that Brian, he will bring the hardware to Munich, and he will create images which you can flash on. And hopefully I can force him or convince him to create some tutorials on that it's a step-by-step instruction. Like, for example, there's this in Berlin, the Freenet initiative was born. So Berlin tries to create an open, uncontrolled, uncensored, parallel internet based on Wi-Fi routers. So there's a set of 50 routers which is supported. You flash a new firmware on it and you configure 3 things. And then it's a mesh network. And again, if a router has internet connection, then it shares that with the same router. Oh, I'm getting some messages. With the same router and also with nearby routers. So that's, I was trying to use it. It's not very stable, but there's the initiative. And yeah, anyway, yeah, that's the idea. And you just need to flash the firmware and add 3 parameters, and you are in. That's the idea, no? For APRS, CB APRS, for PMR 466, and for the LoRa frequencies. Also the Things network. So for example, we are supporting the Things network via Node-RED already. So all those technologies we want to try out, and I'm in contact with the Things network guys in Munich as well. So I hope they bring 1 access point and 1 or 2 devices to the hackathon, and we will do some really cool late night Oktoberfest going out and war driving sessions together.
Romeo, one thing that does sort of seem a challenge is many of the different technologies that you've shown have very different bandwidths and data rates. I can imagine when you start putting a mesh infrastructure where you have sort of duplication, you can very, very quickly build a bottleneck. So do you have some sort of idea how you would manage that within the network? And is it going to be prioritization or drop packets after a length? Or
yeah, so it's all. So it's prioritization. So you have that already, by the way, in APRS. You have 3 levels. One is emergency, and then prio and normal. And you can only congest a cell. No, that's one problem. You can congest the cell, and if you make the cells small enough, that's not a real problem, because you can just occupy the whole frequency with your crappy signal, and then nobody else is going to be received. On the mesh level, it's deduplication. So we are hashing the messages and we are omitting. That's why it's called omit. And also it's a round robin scheme. So for example, if you are connected to 10 peers, you can only flood the node with 10% of the messages. Otherwise, you don't get forwarded anymore. A level above, we are thinking of using asymmetric cryptography. And even someone of the team in Munich thought about using Bitcoin payment channels, where you have to add 1 Satoshi to each transmission, and if you don't do so, you don't get forwarded. So there are a couple of ideas, and I'm happy to work on those end of September. Any comments, Brian? I know you have a lot of experience. If you have.
Yeah, I mean, I'm just thinking things like Sigfox and LoRaWAN. You're actually rate limited as well in terms of being a good citizen in terms of how much data you can send per
yeah.
day. So it's quite an interesting scheme that if you rely on a specific link that's potentially restrained.
Yeah, that's true. So that's why you have to use prioritization, and also even APIs, it's very limited on the rate. So it's not meant for YouTube streaming. It's meant for getting a short message in an emergency use case from A to B. And even that JT65 and FT8 technology, it's even very, very slow. It needs, I don't know, so JT65 needs, I think, for 20 characters, it needs 1 minute. FT8 is, I think, 4 or 8 times as no, four times as fast. AFSK is 2,200 byte per second, and if you are using FSK on the low frequency band, if you want to be more error resistant, you can go down to 300 bytes per second. So it's really made for like SMS stylish transfer. Also the Things network and sub-gigahertz, I think, is also limited to those ballparks now.
Yeah. No. I think you're going to have some very interesting challenges to solve.
Yeah. Otherwise, it's getting boring, no?
All right. Well, that's brilliant. Thank you, Romeo.
Welcome.
So if there's no other questions, we'll end the call here. Great example of how we can apply this towards a call for code set of projects. All right. Thanks, everyone. Thank you, Romeo.
Thank you.
That was brilliant. And we'll stop the recording here.